So how did that second exam go for you? I felt like Professor Wu was really trying to trip us up this time.
Not too bad, actually. I think making these deep dives is really helping me lock down these concepts, you know? It's kind of like having a study session with a buddy, but with like a recording to help you remember.
Yeah, for sure. It really is crazy how just talking through something can make it click.
It really is.
Speaking of clicking, today we're going to be diving into linear discriminant analysis.
LDA.
LDA, yeah, which has been popping up all over the place in this machine learning course.
Yeah, it's a pretty cool algorithm for dimensionality reduction. You know how we've been using PCA to simplify our data? Well, LDA takes a slightly different approach.
Okay.
It's especially useful when we're dealing with labeled data and classification problems.
Okay, so let's break that down a little bit. How is LDA different from PCA? Because they both seem to be about reducing dimensions, right?
Yeah, exactly.
Yeah.
Imagine you're trying to project a 3D object onto a flat surface, right? PCA, its goal is to try and preserve the overall shape of that object in that 2D projection, like capturing its shadow. It's concerned with maximizing variance, finding those directions in the data that contain the most information.
Okay, so if we had like a bunch of orange and green dots representing different categories, PCA might draw a line through them that mixes them all up, making it hard to tell the orange and green groups apart.
Exactly. And that's where LDA steps in. Instead of just blindly reducing dimensions like PCA, LDA uses those labels in the data to kind of guide that projection. It wants to find that projection that maximizes the separation between those orange and green clusters while keeping the clusters themselves as tight and compact as possible.
So it's like LDA is playing this balancing act. It's got this dual mandate.
Yeah.
Push those clusters apart while at the same time making them as internally consistent as possible.
Yes, exactly. Think about it like you're trying to separate two piles of sand, one orange, one green.
Okay.
First, you want to push those piles as far apart as possible, you know, to create that clear distinction.
Right.
Then you want to kind of pack each pile tightly so that the grains of sand within each pile stay close together.
Okay, I'm starting to see the difference here. So LDA is like PCA, but with this extra layer of like strategy that uses those labels to improve classification.
Yeah.
But how does it actually work? Is there a ton of like complex math going on behind the scenes?
Yeah, there is some math involved.
Okay.
But the overall objective is surprisingly similar to PCA. It all comes down to finding that optimal way to project the data.
And I remember Professor Wu talking about eigen decomposition in his lecture on LDA. Is that what we're talking about here?
Yes. Both PCA and LDA leverage eigendecomposition to find those optimal projection directions.
Okay.
That key difference is really how they define the special matrix, sometimes called the Q matrix.
Okay.
And that kind of guides the eigendecomposition process.
Gotcha. So they're both using the same tool, but LDA is using it with a slightly different blueprint, one that's designed to separate those clusters as clearly as possible.
Exactly. You got it.
Okay, cool.
In TCA, the Q matrix is simply the covariance matrix of the data.
Yeah.
It's all about finding directions of maximum variance. But in LDA, the Q matrix is defined in a more kind of nuanced way.
Okay.
Taking into account both the separation between clusters and the variance within each cluster.
So that sounds pretty complex. How does LDA actually like quantify that separation and variance?
Well, LDA uses something called the between class scatter matrix, which we'll call S1 to represent the separation between those orange and green clusters. It's like measuring how far apart those sand piles are.
Okay, and so for the variance within each cluster, LDA uses the within class scatter matrix, or S2.
Yes.
And that's like measuring how compact each sand pile is.
Precisely.
Right.
And LDA cleverly combines these two matrices to form that special Q matrix I mentioned earlier.
So is the Q matrix just a straight up addition of S1 and S2?
Not quite. LDA actually takes that S1 matrix and multiplies it by the inverse of the S2 matrix.
Okay.
And that way, the separation between clusters is emphasized, while the variance within each cluster is minimized.
It's like saying, we want those sand piles far apart, but we also want each pile to be super compact.
That's a great way to put it. It's this carefully crafted Q matrix that makes LDA so effective at separating labeled data for classification.
This is really interesting. So we have these scatter matrices that represent cluster separation and compactness. They get combined into this special Q matrix, which then guides that eigen decomposition process.
Right.
But how do we actually get from those matrices to the final projection?
Well, that's where those eigen things come in. Remember how eigenvectors tell us the directions of greatest variance in PCA?
Yeah, they're like those arrows pointing in the direction of the data's biggest stretch.
Right. LDA uses the eigenvectors of that carefully constructed Q matrix to determine the best projection directions, just like PCA.
Okay.
But the key difference is that LDA's eigenvectors are specifically tuned to find the directions that best separate those labeled clusters.
So this is really starting to make sense now. LDA isn't just randomly picking a projection.
No.
It's using information about the relationships between variables and the distribution of data points within each class to make like a more strategic decision.
Exactly. It's all about finding that projection that maximizes separability, making it way easier to distinguish between those labeled groups like our orange and green dots.
This is really helpful. I feel like I'm finally getting a handle on the basic logic behind LDA.
Me too. But there's so much more to explore here.
Oh, yeah.
Remember how Professor Wu kept emphasizing the concept of batch projection in his lecture?
Yeah.
Turns out that's a super helpful foundation for understanding LDA's inner workings.
Batch projection. So that's about projecting a whole bunch of data points onto a line or a vector at the same time.
Exactly. And it's a core concept that helps us visualize how LDA actually projects data to achieve that, beautiful cluster separation.
I'm definitely interested in digging deeper into that.
Me too.
But I think for now we're going to have to leave it there.
Yeah, sounds good. Okay, so you ready to jump back into batch projection?
Yeah, definitely. I'm really curious to see how it all connects to LDA.
So remember how batch projection allows us to project, a whole set of data points onto a specific line or a vector all at once? Well, that's basically what LDA does, just with a little bit more finesse.
Okay, so we've got our data points kind of scattered all over the place.
Right.
And we've got our projection vector, which LDA has carefully chosen, to maximize that cluster separation. And then, bam, we project all those points onto that line using batch projection.
Exactly. And what's cool about batch projection is that it can be done super efficiently using matrix operations.
Right.
And this becomes really important when you're dealing with these real world data sets that can have thousands or even millions of data points.
Yeah, I can imagine. It would be a nightmare to try and project each point individually if you had a massive data set.
Yeah.
But I'm still a little fuzzy on how this all ties back to those S1 and S2 matrices, the ones that quantify the separation and compactness of our clusters.
Great question. So remember how we talked about how LDA combines S1 and S2 into that special Q matrix to guide that eigen decomposition?
Yeah, that Q matrix seems to be the key to LDA's magic.
Well, it turns out that those S1 and S2 matrices are actually derived from the covariance matrix of the data.
Ah, the covariance matrix.
Yeah.
The one that tells us how different variables in our data set are related to each other.
Exactly. And it's that covariance matrix that provides that kind of raw material for calculating those S1 and S2 scatter matrices.
So it's like a chain reaction. We start with that covariance matrix, use it to calculate S1 and S2.
Yeah.
Then combine those into the Q matrix. And finally, use the Q matrix to guide eigen decomposition and find those optimal projection directions.
You got it. It's this beautifully orchestrated process that uses the power of linear algebra to separate those labeled clusters in the most effective way possible.
Okay, now this is really clicking for me. So LDA isn't just randomly choosing a projection.
Nope.
It's using information about the relationships between variables and the distribution of data points within each class to kind of make a more strategic decision about that projection.
Exactly. It's all about finding that projection that maximizes separability, making it easier to distinguish between those labeled groups, like our orange and green dots.
Okay, I think I'm ready to see how this would actually play out, in a real-world scenario.
Yeah.
Can you give me an example of how LDA might be used in practice?
Absolutely. Let's imagine we're working on a facial recognition system.
Okay.
Our goal is to build a model that can accurately identify different people based on their facial features.
So our data points would be images of faces.
Right.
And each face would have a label, correspondent to the person's identity.
Exactly. Now, those raw images, they contain a ton of data.
Right. Each pixel is a variable.
Mm-hmm.
And we could have hundreds of thousands of pixels in a single image.
That's a lot of dimension.
Yeah, way too many for our model to handle efficiently.
Right.
And that's where LDA comes in. We can use LDA to reduce the dimensionality of those facial images while still preserving that information that's most relevant for distinguishing between different individuals.
So instead of looking at every single pixel, LDA will find a smaller set of features that best capture like the unique characteristics of each person's face.
Well, exactly. LDA will analyze those relationships between all those pixels, taking into account those labels we've provided for each face.
Okay.
It will then project those high-dimensional images onto a lower-dimensional space, creating this set of features that maximize the separation between different individuals, while minimizing that variation within each person's facial features.
Wow. So LDA is like a super smart feature extractor for facial recognition.
Yeah.
He's taken all that messy pixel data and transforming it into a clean, concise set of features that are, like, optimized for classification.
You got it. And the same principle can be applied to a bunch of other domains, from, medical diagnosis to spam filtering to handwriting recognition. Anywhere you have labeled data and want to find that best way to separate those categories, LDA can be a really powerful tool.
Wow. So LDA is way more versatile than I initially thought. It's like a secret weapon for making sense of complex, high-dimensional data.
It really is. And the best part is that it's built on this solid mathematical foundation, making it a reliable and interpretable method for dimensionality reduction and classification.
This has been a really insightful deep dive. I feel like LDA has gone from this mysterious algorithm to a powerful tool that I can actually understand and appreciate.
Me too. It's amazing how exploring the underlying logic of these methods can kind of demystify them and make them feel a lot more approachable.
Okay, so we've talked about how LDA is up to PCA, but with this special focus on separating different classes. Right. And we've even seen how it can be a total game changer in things like facial recognition, taking all those pixels and turning them into useful features for identifying people. But I'm kind of curious about the assumptions behind LDA. Does it work equally well with all types of data?
That's a great question. Like most statistical methods, LDA does have some assumptions that are important to think about. For example, LDA assumes that the data for each class follows what's called a Gaussian distribution.
Gaussian distribution. Now, remind me what that is again.
So think about that classic bell curve.
Okay.
That's a Gaussian distribution.
Right.
It basically means that the data points are more likely to cluster around that average value, with fewer data points further away from the average.
Right, like height in a population. Most people are around average height, with fewer people being very tall or very short.
Exactly. So LDA assumes that each class of data has that kind of bell-shaped distribution.
Okay.
And if our data doesn't quite fit that assumption, then LDA might not be the best choice.
So it's kind of like trying to fit square pegs into round holes.
Yeah.
If our data has a completely different shape, LDA might not be able to capture those underlying patterns effectively.
Yeah, that's a great analogy. It's always important to understand the assumptions of any statistical method before you actually apply it. We want to make sure our data is going to play nicely with the algorithm we choose.
That makes a lot of sense. So what are some other things to keep in mind when we're working with LDA?
Well, another important thing to consider is the number of dimensions that LDA can actually handle.
Okay.
So LDA can reduce dimensionality down to the number of classes minus 1.
Okay, so if we have 3 classes, like cats, dogs, and birds, in like an image classification problem, we can reduce the data down to just 2 dimensions.
Exactly. And that makes it super useful for visualizing our data on a 2D plot. We can actually see how well LDA has separated those classes just by plotting them on a simple graph.
I see. I'm really starting to see how all these pieces fit together now. LDA is like a puzzle where understanding each piece helps us appreciate that bigger picture.
Yeah, it really is. And it's just one example of all the incredible tools that are out there in the world of machine learning.
Right.
The more we understand these algorithms, the better equipped we are to kind of unlock those secrets that are hidden within our data.
Well said. Thanks for taking us on this deep dive into LDA. I feel like I've gained a whole new appreciation for this powerful algorithm.
You're welcome. It was great exploring the depths of LDA with you today.